We are going to look at a challenging thermal physics question for year 13 physics. Pause the video now and try both parts of this question. Part A asks to find the specific heat capacity of liquid nitrogen. So we've got to read the question carefully here to understand all the bits of information we've given and the full calculation. So we've got a cylinder that's containing some nitrogen. It contains this much mass of nitrogen. It starts at this temperature, and we've got a heater heating it at a constant rate of 18 watts. And then we've got a constant pressure during this heating process. It says it's heated from 70 Kelvin and it turns into a gas completely after this much time. And then in this information here, we know that the boiling point is this 77 Kelvin. So what is happening? There's being some energy supplied, and that energy that is being supplied goes into both the heating and the state change. So we've got two calculations we need to do. We need to say that the total thermal energy supplied goes into the heating, which is going to be given by mc delta theta, plus the state change, which is ml, and it's boiling, so for being technically correct, latent heat of vaporization. How much energy is supplied in total? It's going to be energy times time, because we know we've been given a power and we've been given a time. So the energy supplied is 18 watts times by 1335. That's going to go into the temperature change, so 0.075 times by the heat capacity that's what we're trying to work out, isn't it? And the temperature change is 77 minus 70, which obviously is 7, but I'm just going to write that in so it's really clear to the examiner I know what I'm doing, plus the mass times by the latent heat of vaporization. So now it's a case of solving for C. So really I should rewrite this C equals, in fact I should have done that here, C equals, but this is also clear enough. So let's work out the answer. So I've got 17,200 joules per kilogram per Kelvin or per degree Celsius. Okay, very often they do ask you for a unit. It's really easy to work out the unit. You obviously just rearrange for heat capacity Q over m delta theta, and you go, right, what is the unit? Well, it's obviously going to be joules per kilogram per degree Celsius or per degree Kelvin. They don't really mind which one you use. Part B. This is quite tricky, this one. You've really got to think this one through. So what is greater, W or Q? So W is the work done by the nitrogen in the cylinder when expanding due to a change of state, and the energy required to change a state is Q. So let's think about Q. So the change of state. So that is pretty simple, isn't it? That's mLV, which is 0.075 times by the latent heat, which is 2 times 10 to the 5. 0.075 times by 2 times 10 to the 5, which is 15,000 joules, and this equals Q. So I haven't done it, in the order necessarily that suggests, but that's because I'm picking the easiest bit first. Right? It's always good to start with the easy bits, helps your brain warm up, and you guarantee yourself some marks. This would be, 4 or 5 marks, this question. What about W? That's the work done when expanding. So obviously you know that the work done when expanding at a constant pressure, and we know it's a constant pressure because it tells us that in the question up here, is pressure times change in volume. So the pressure is 1.2 times 10 to the 5 pascals times by the change in volume. Now, what is the change in volume? We haven't been given the change in volume. So we need to work that out. We need to work out the volume of the gas and the volume of the liquid, and then we obviously subtract one from the other. So we've been given the density of liquid nitrogen and density of nitrogen gas, and we've also been given the mass. So we know that density is mass over volume. Okay, in your exam, please do not, write down random formulas all over the place. It's not clear at all. But I just want to write this down here in case you need to visualize rearranging it. So the volume is going to be the mass over the density, and that's obviously the mass of the gas, and this will be the mass of the liquid over the density. So we've got 0.075, right? The mass is obviously fixed and doesn't change, over the density of the gas, which is 3.8. So that's 0.020 meters cubed, and the density, so the volume of the liquid is going to be 0.075 over 810. Which is, that's quite a lot smaller, isn't it? 9.1 times 10 to the minus 4 meters cubed. So now the change in volume is going to be 0.02 times, minus 1 times 10 to the minus 4. Which is 0.020 meters cubed. So then I can put that in here, 1.2 times 10 to the 5 times by 0.02. And I get 2,400. Now, if you got a slightly different answer, that might be because of rounding. Okay? I have rounded a couple of times here, and I've also rounded here. It's actually 2388 when I did it. So you might have a slightly different answer. That's fine. So this is joules. What do we notice? W is a lot less than Q. So I'd write somewhere else. I'd say 2,400 is less than 15,000. So W is less than Q.